It's time to start integration. So one thing you should know is at this point in the semester, we're now going to assume that we know how to take derivatives. We've done the derivative section. So whenever we have a function like x squared, we can just automatically make that 2x. And similarly, we'll be able to do antiderivatives. So these are not things that you need to be worrying about or proving in the middle of your proof. You can be using those as we go through the section. But when we think about integration, what we're really thinking about is this kind of idea of accumulating area. We're going to use area kind of as the idea to build our way through the section. But as you know, we don't want to rely too much on these kind of intuitive ideas of what's going on. Instead, we want to really focus ourselves on the actual definitions, because sometimes some things can happen that are a little strange, and we'll see a couple of those. Okay, so whenever we think about integration, we should always have some picture that looks something like this in our head, where we have kind of our function, and then we've got a and b. And what are we going to do? Well, we're going to chop up this function into pieces, and we've all seen this happen in calculus class. And then we'll, take some estimates on here and draw different estimates. And the way we're going to do it right now is we're going to begin with upper and lower estimates. And so what you'll see is the difference between the upper and lower estimates are these things right here. And the question is, can we make that difference as small as possible? And so what you'll see our definition is going to turn out to is we're going to define an upper limit on the area. Then we'll define a lower limit on the area. And then we'll say if that upper and lower are less than epsilon, if you by making these these intervals small enough, then we'll say that the limit actually exists. But we're going to do this in as general language as possible. So we're going to try to be as open to different ways of interpreting this as possible. So to start, we're going to think about a partition. And what is a partition? A partition of some set AB is really just a set of points. It is just a set of points. We'll call it x0, x1, all the way up to xn. And the important thing is that x0, such that x0 is a, and x0 is equal to a, and that one is less than x1, which is less than x2, which is less than. And so we want each point to be getting strictly bigger until we get to the other side, which is b. So coming back to our picture over here, our partition here, this would have been x0, x1, x2, x3, and x4. So our partition would have been these numbers on the x-axis. So whatever we named these x-axis numbers, that would have been our partition. So it's kind of giving us those values. Notice we don't claim that each value has to be the same width apart. So this one could have a size, this one could have 1 unit, this could be 1.5 units, this one could be 2 units. So we don't claim that they're all the same distance apart like we often do in calculus class. Okay, but this is what we mean when we say a partition. And a partition has a norm, which is a way of measuring the size. So we'll call the norm of that partition, we will write it with double bars like this. And so the norm of partition is really just going to be the widest interval among any of those partitions. So it's just the max for the max over all of the j's. I'll just say the max over all the j values of xj minus xj minus 1. So the norm is just measuring each of those distances that I mentioned just a little bit ago and saying which one is the largest. And so if the norm is 5, then that means every interval that we have is 5 or less. So it's a way of kind of, you can see that we're really looking for an upper bound. We want to know the maximum distance between all of these things. Okay, so that's the idea of the norm. And finally, the last thing we're going to talk about is what we call a refinement. And a refinement is what happens when we make our partition more precise than the one right before it. So a refinement, which we will call Q, is always a subset of P. Oh, wait, no. P is always P is always a subset of Q. And so Q is some set of numbers. Let's call Q, I don't know, we can give them different letters. Y0, Y1, Y2, dot, 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 up to Yn. And what you'll notice is that Q is also a partition, and P is contained in Q. So that means that this one is going to be X0. One of these other ones is maybe X1. And then maybe this is our X in. I probably should have used a different letter here instead of in, because those aren't necessarily the same. So that's supposed to be an M, that thing. So what would that look like? That would look like if I was making a refinement, then I would take these, I would keep these X values that I've already got, and then I would add some others in. Okay, so Q is this collection, which is a larger collection, but with all of the P's contained inside of it. So we'll use kind of this set notation that we have right here to describe what it means to be a refinement. Now, I want to make some observations. So some observations is if we have, and by the way, we will use the phrase that Q is finer than P. So, by the way, if you have two partitions, one doesn't have to be finer than the other one. So, for example, if I have the interval from 0 to 1, one partition I could use could be 0, 1/2, and 1. So my partition could be the partition 0, 1/2, and 1. Notice the 0 and the 1 have to be in any other partition, in any partition we choose. Another partition, we could be 0, 1/3, 2/3, and 1. So this is how I might write those two partitions down. And notice that there's no relationship to them. So P is not finer than Q, and Q is not finer than P. So they're really not connected to each other in that way. I could, however, if I wanted, I could change my Q to be something different. So for example, if I changed my Q to be 1/3, 1/2, 2/3, and 1. So if I just add a 1/2 in there, then all of a sudden Q does contain P. And so this is a refinement. So all I've done is I've added 2 marks inside my P refinement to make it more precise. It turns out that there's one refinement, which is, tends to be one of the most commonly used examples, and this is called the dyadic partition. And the dyadic partition is just the partition that's the set J divided by 2 to the n. So let's think about what the dyadic partition would be. It's a partition of 0, 1, but we could generalize this to other regions if we want. And so what does the dyadic partition look like? Well, this would be the n equals 0 opportunity, right? So n equals 0, which is 0 and 1. If I add 1, we include a half in it. So notice if I have 1, we would have 0, a half, and 1. If I do n squared, then that's a fourth. I would have 0, 1/4, 1/2, and 3/4. And notice what I'm really doing is it's like I'm dividing by halves. So then if I did one more, I would have an eighth, a fourth, 3/8, a half, 5/8, 3/4, and 7/8. And so, for example, that would be a partition that I just drew would be P3, right? Because that would be all the powers, every multiple of 8, right? So it'd be 0/8, 1/8, 2/8, 3/8, 4/8, all the way up to 8/8. It's written a little bit more detail in the book. I was a little bit lazier. But one thing that's nice about this partition, there are two things that are really nice about this partition. Item number 1 is that what happens to the norm of these partitions as n goes to infinity the norm of the partitions is going to 0 because we can see these partitions are shrinking and getting smaller and smaller. So that's a really nice property of this partition. Another really nice property of this partition is that each partition is finer than the one right before it. So they're each refinements of the previous partition, which is good. So these are two nice properties that if you're trying to show some things are integrable, this ends up being a fairly useful partition to use. Okay, once we have the idea of partitions, we're really going with the idea of upper and lower sums like we had earlier. And we will call them, the book says upper Riemann sum. I think I'm going to throw the word Riemann out because it feels like it's a little confusing because we're going to use the Riemann sum in the next video, and it's going to be slightly different than this one, although they're close to each other. The upper sum of a function f over a partition p. Now, we have to know some things, right? So we have to know that we have an interval. So we're always on some interval AB. And when we talk about integrals, we'll always be talking about integrals on an interval from A to B. By the way, when you want to do other types of problems, or when you want to get kind of really strange functions or change your intervals around, that's when life gets a lot more interesting. And this kind of leads us into a field called measure theory and all sorts of interesting alternate ways of thinking about integration. And that's one of the big topics in real analysis 2. So if you're wondering what you might do in real analysis 2, you might take this idea and make it explode by saying, well, what would be over the integral over, say, just the rational numbers or something? And that's confusing what that means. So you have to kind of define these things and then go forward with your with those conclusions. Okay, but this is we're going to do the upper sum. So we're working on an interval. We have a bounded function. So one important thing on here is we always want f to be bounded, and if f is not bounded, then we're not going to be talking about it in this section. It's not until we get to improper integrals that we're going to even think about unbounded f's. Okay, so whenever we talk about the upper sum, we're going to use this notation. We're just going to use a u with an f and capital P. And this is just telling us that we're taking an upper sum, the f is the function, and p is the partition. And all we're going to define this to be is the sum over all of the partitions, 1 to n, of capital Mj of f times delta xj. Okay, well, I added some new letters in here, so we should ask, what are they? So you should probably be asking, what is this mj and what is this delta j? Well, mj is the sup, mj of f. The book likes to think of them as functions of the function, which I guess is not the worst way to think about them, which is the sup of f over that interval, which is the sup of f over the interval xj minus 1 to xj, and so it's just the largest f value in that integral, and our delta xj is just going to be xj minus xj minus 1. So all we've really done is we've taken that picture, and so if we go back to the very beginning, we've taken that picture and we've defined like an xj minus 1 and an xj, and then we looked in that interval and said, what's the largest value? And if this is the largest value, then we've used that largest value to compute our area. And so you can see that we're still kind of getting that area and that integral idea that we were going for. So you see we've got the height times the width. And so m is like the height. It's like the largest possible height in the entire interval. And then the width is this delta j term. The lower sum is pretty similar. So there's not a big difference between the upper and the lower sums. Okay, so we're going to need this as we go through the series. Let's go ahead and talk about what do we mean when we talk about a series telescoping. Many of you will have heard this already or kind of be familiar with this. But telescoping is just when we have some series that looks like this, and the book likes the letter J. The letter likes to use g of k plus 1 minus g of k, as k goes from, say, m to n. So the question is, what happens when I do a series like this where I have the same function giving outputs that are one apart from each other? Well, let's just write out these series real quick, and you'll notice when I put the first term in, I'll get g of m plus 1 minus g of m. And then when I put the second term in, I'll get g of, now it'll be m plus 1, g of m plus 2 minus g of m plus 1. And then we'll kind of keep going all the way across until we get to the very last one, which is g of n. And so we'll have g of n plus 1 minus g of n. And so now if we look at this carefully, what you'll see is that, well, this m plus 1 right here and this m are the same term, and one is positive, one's negative, so those two are going to cancel. Similarly, I will have an m plus 2 term here in this next phrase that's going to be positive, and it's going to be negative, and it's going to cancel with that positive. And what you'll see is that every single term is going to cancel except that very first one and that very last one. So every term cancels with each other, and that's what we call telescoping. So when you get the positive, negative, and you get the terms, all the middle terms canceling out, and you only have the first and last terms left. So when they telescope, our answer is g of n. Oh, sorry, I circled the wrong one here at the end. That should have been the one that survived. That should have been the one that canceled. Okay, we get g of n plus 1 minus g of m. Notice it's the bigger one that survived, right? Not the smaller one canceled with the g of m in the term right before it. So the very largest term, which is that g of n plus 1 and g of m. Okay, this will just be a nice little tool that we use. We've already used it once, but it's going to happen so much in this section, in the next section, and the next section that we'll just say it's telescoping, and therefore we know what the answer is going to be. Okay, let's take a little bit and think about some properties of these U's and L's. And we have bunches of kind of theorems and things to go with it. I'm not going to kill myself proving them, but one important thing is that if you're given any partition, what should be the relationship between the lower and the upper sums of the partition? Well, the upper sum is always using a sup over the interval. The lower sum is always using an inf over the interval. So that means that your upper sum is always going to be larger than your lower sum. And this is a nice proof because this lets us kind of group these into separate categories. A nice theorem is what happens if you take a refinement. So if Q is a refinement of P, then, and this is what our theorem is going to say, that whenever you take your refinement, your lower sums become bigger and your upper sums become lower. So this is the idea. So refinements make lower sums bigger and bigger sums lower. And this makes sense because this is kind of what you think would happen if you go back to calculus class and you draw a bunch of those rectangles. As you add more and more rectangles, your lower estimates become larger, your larger estimates become lower, and the two kind of meet in the middle wherever the actual area is. Well, this theorem is kind of trying to get at that idea. And so what's the big idea here? Well, what you'll notice is this part is got to be true based on what we said above. So really the only thing that's difficult, the only thing left to really prove is that if you take an upper sum and refine it, you get a number that's smaller. So let's talk about how might we prove that. So let's just clear this page and let's just talk about that question of, can we prove that if you have an upper sum and you take a refinement of it, that you get a number that's less than the upper sum from the original? And really the question is, with a refinement, is what happens if you have an interval. Let's just take an interval from A to B. What happens when you have that interval and you add a point in the middle of it? So what's going to happen in this? And notice, if we can show that that the lower sum is smaller when you add 1 point, then any refinement is just adding a finite number of points. So you just add 1 point, and then add another point, and add another point, and add another point, and you've done your problem. So we're just going to ask kind of this basic question, and that is it true that that adding 1 point makes your upper sum potentially smaller, either smaller or the same size? Well, it probably should be. And the reason why it should be is let's ask, what is the upper sum with our p here? The upper sum of f and p is, well, we defined this earlier. It is if we only have one interval, it's going to be the sup over that entire interval of, let's see, how did I, what notation did I use? Let make sure I get my notation correct, so I don't confuse this all. Okay, so it's going to be that m, since there's only one of them, I'll just call it m of f, and then delta, and since there's only one interval, we'll call it x, and so that m is going to be the sup of f of that interval of f from a to b. And then that delta x is just b minus a. That's that interval right there. Well, now let's ask about what happens if I do it for q. Then it's that, well, now we have two sections. We have an a to x naught and an x naught to b section. So it's m1 of f, and we'll call it delta x1, plus m2 of f, delta x2. So all we did is now we have two things to add together. And those two things add together end up being the sup of f over the interval a to x naught times b times x naught minus a, because that's that interval, plus, and then this is our second m value, is going to be the sup of f from x naught to b times b minus x naught. So all I did was do the exact same computation twice. But let's look really closely. Notice that the sup, so I'm going to come over here and write a little detail over here. Let's write the detail up here in this section. So my little details, notice that if we have two intervals, and I1 is a subset of I2, then the sup over I1 has to be less than or equal to the sup, of f over the interval I2, right? And that's because I2 has gotten bigger, so you've only added more points, and if you added more points, the only thing you could have done is make that sup go up. You couldn't have possibly made it go down by adding more points. So the smaller interval always has a lower sup than the interval that contains it. Well, that's what we just have to notice here, and notice that this sup has to be less than this one, because this only goes halfway from a to x naught versus this one, which goes a all the way to b. Similarly, this one has to be less than that one. So now I can make my inequality, and my inequality says that this is less than m times x naught minus a plus m times b minus x naught. But now if I factor my x naughts out, or factor my m's out, you see my x naughts cancel, and so this is m times b minus a. And so what we got, and that was what the original upper sum. So basically what we see is that as you add points to your points to your partition, and you get a refinement of that partition, the refinement just takes the intervals that you were taking the sup of. So these intervals that you were taking the sup, it just makes them into smaller intervals. And since they're smaller intervals, the sups could potentially be smaller. Now, they could be the same size, but they could be smaller. But when we add up these outside edges, they're all adding up to the same thing that they were just a moment ago. Okay, so this kind of ends that proof. If you want more details, you can read it in the book. This is 5.7. But what's nice about that is if you make a is that if you take a refinement, then all of a sudden your upper sum gets smaller and your lower sum gets greater. Okay, one last thing to notice, and that is, well, what if we have two different refinements. So what if I have a lower sum of f over one type of refinement, or one type of partition, and then I have an upper sum over a completely different partition? Then what do I do? Well, the answer comes from what we did just a second ago, and that is we can find a partition which is a refinement of both of these. So how do I do that? Well, you just take all the elements from P1 and add them to all the elements of P2. So we just take the union of these two things and group them together. So this is a refinement of both P1 and P2. Well, that's nice because that kind of shows us how the proof is going to go, because that means that our LL has to be less than L over this refinement, right? So it has a common refinement. So based on the theorem we just did a second ago, the lower sum has gotten larger when you go to Q. But at Q, that lower sum has to be less than or equal to the upper sum because it's the same refinement. But then the upper sum has only gotten smaller when we went from P2 to Q. And so that means this is U of F P2. So we see that we can use this common refinement that they have between them in order to compare the two outside edges. So this tells us what should be the relationship between these two. The lower sum should be less than the upper sum. Okay, so finally, we're ready to kind of talk about what it means to be integrable. So we'll say a function is integrable on some closed set AB, and we'll sometimes we'll call this Riemann integrable, but we'll have a different definition of an integrable in the next video, and we'll show that they're actually the same definition. But so what does it mean to be integrable? Well, it means that you can make the difference between our lower and upper sums as small as possible. So we will say it like this: if for every epsilon greater than 0, there exists some partition such that UFP minus LFP is less than epsilon. Notice I could have included absolute values, but because we know U is bigger than L, the absolute values are a little unnecessary because we already know this is a positive thing. Okay, so this is exactly what it means to, so integrable just means that that upper sum and that lower sum can be made less than epsilon for any sequence we could possibly want. All right, so now let's spend a little bit of time exploring this difference between integrability and continuity. And you might be able to go ahead and guess the answer, and that is, as long as it's continuous, it must be integrable. But it turns out that that's not enough, that there are a lot of functions that are not continuous that are still integrable. And so we'll talk about all these things in just a minute. But let's do that first theorem first. If f is continuous on AB, then that means f is integrable on AB. Okay, so this is going to be our first proof. And so if I'm going to do this proof, what am I going to do? Well, I'm going to start with an epsilon, and then I'm going to show that it must be smaller than 0. Okay, so the first thing I'm going to do is I'm going to let epsilon be greater than 0. And this is where we use something from just the last couple class periods. And we know that f is continuous on a closed interval. Well, since the interval is closed, that means f is uniformly continuous on that closed interval. Well, that's nice because uniform continuity means I can use the same delta value throughout the whole region. So what this means is that if, so now what I can do, since I let delta be greater than 0, then that means, or I let epsilon be greater than 0, then there exists a delta such that if x minus y is less than delta, then f of x minus f of y is less than, and I would normally put epsilon, but now I'm going to put epsilon divided by b minus a, and that's because what's going to happen is we're going to have we're going to add up a bunch of these things, and each one is going to be less than epsilon, but then we're also going to have to add the whole region together. Okay, so now what we have to do is we just have to let P be a partition. Partition doesn't start with a B, does it? Let P be a partition such that the norm of P is less than delta. Okay, so we're going to take some partition, and we're going to make sure that every single piece of our partition is less than delta. Why are we doing that? We're doing that so that we can know that this property from uniform continuity must be true, so that this difference between the f values must be true. And that's how we're going to bound everything and make everything go the way we want it to be. Okay, so what I know is that if I just take one interval, so on some interval, say xj to xj minus 1, what is the maximum of this? Well, I know that, hold on just a second, okay. Okay, so on one of these intervals, then I know that the maximum has to actually exist as a point in the interval, and so does the minimum. So let's see. This seems unnecessary the way the textbook's doing this. Give me just a second, because I don't really want to follow their proof. I'm gonna try to do it for myself, and I think this will make sense. Okay, so that partition is going to be x0, x1, dot, 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 up to xn. And so now the question is, well, what is my upper sum of all of these, and what is my lower sum of all of these? And importantly, let's ask, what is the upper sum minus the lower sum of these guys? Well, my upper sum is the sum of all the maximum values of each interval. So let's say j goes from 1 to n of the maximum values of each interval times the size of the interval. And then the lower sum is the inf over the interval times the lower value of the interval. But now notice what this is. This is just the single sum, and I can factor out my deltas of whatever my maximums minus my minimums were on each interval. Let me get some empty space to talk about up here. And then what I'll notice is I'll just make an observation real quick. And my observation is that because I know that xj minus xj minus 1 is less than delta, what does that mean? That means that f of xj, that means if I take whatever the maximum and minimum values are in that point, in that interval, that means that the maximum value, f of x capital M minus f of x little m, must be less than this epsilon over b minus a. And this is why, I guess maybe I shouldn't have departed from the textbook so much. This is why the textbook said that these points have to exist by the extreme value theorem. So let's go ahead and say that. And we know by the extreme value theorem, xm equal to the max on xj minus 1 to xj, and x little m equal to the minimum on xj minus 1 xj exist. And probably I should have written that beforehand. Sorry, this is why whenever I was a student, I would always sketch everything out on a scratch newspaper before trying to write it down, because then I can get things arranged in the order that I want. Okay, so I have this sum, but what's important is this sum, mj minus 1, now must be times delta j Sorry, I'm struggling with my colors here. Okay, times delta J. Well, that must be less than the sum of epsilon over b minus a times delta J, delta xj. But what's important is these delta xj's telescope, right? These telescope, and these epsilons come out in front, so this is actually just epsilon times the very last term in the telescoping series, which is b, minus the very first term in the epsilon series, which is a, and then that cancels out with my b minus a, which is epsilon. So what you see is that if it's continuous, then we can say it's uniformly continuous. We can use this epsilon b minus a. We can use the fact that the max and mins must be bounded by this epsilon b minus a to get that the whole sum is less than epsilon. Okay, sorry about that. I stumbled through that a little bit today. Again, sorry about that. I hope that that wasn't too confusing. Okay. But as I said, that's what it means to be integrable. And now let's make a couple important observations before we move on. And the important observations are this: it's that there are continuous functions that aren't continuous can be non-integrable. So let's do an example. So how about this function that looks like this? F of x equals, let's say 0 from 0 to a half, and then 1 from a half to 1. I'll tell you what, let's not do less. Okay. And so here we go. So this is our integral, and so our function is, here's a half here, and so half is right there. It's right here. It's that value, and then we jump up to 1, and we have an open circle, and it looks like that. So this is our function. Notice it's obviously discontinuous because it obviously has that big jump at a half. So here's the question: is this thing integrable? The answer is yes. This thing still is integrable, and the way we do that is we just make a partition that makes our upper and lower small enough. So what is my partition going to be? Well, I'm going to let epsilon be greater than 0. And all I'm going to do is I'm going to partition it where I make this section and this section. So I'm basically going to just cut out the middle and make this so small that it no longer matters, right? So I'm going to make this super, super small. And then on the right and left-hand sides, it doesn't really matter. So let epsilon be greater than 0, and then let my partition be the partition 0, 1/2 minus epsilon over 2, 1/2 plus epsilon over 2, 1. And so this is my partition. And then let's ask, what is my upper and my lower? So notice I've got 3 sections. So my upper Riemann sum on this, well, on the first section is going to be let's call this M0 delta x0. Maybe I should call it 1. M1 delta x1 plus M2 delta x2 plus M3 delta x3. And now what is that going to be? Well, okay, so it is. Maybe I should have made these. Yeah, let's fix this. Let's make these epsilons over 4. It'll look a little prettier, I think, if I do this. Epsilon over 4, and then 1 plus. Okay, let's just rewrite it all. 1 minus epsilon over 4, and 1 plus epsilon over 4. Oh, and I changed my colors. Okay. Well, I can't. I can deal with having the wrong colors. Okay, so if I look at my first interval from x0 to x1, my maximum value is 0, and my delta x value is just 1 minus epsilon over 4, or 1/2 minus epsilon over 4. Plus, now if I look at this middle term, my maximum is actually 1, so it's 1 times 1/2, or times epsilon over 2. 1/2 times epsilon over 2. And now if I look at this last term, the maximum value is 1, and its distance is 1/2 minus epsilon over 4. So what is my upper? When I put it all together, my upper is epsilon over 2 plus 1 times 1/2 minus epsilon over 4. Okay, what's my lower going to be? My lower, let's skip a little bit of the notation. My lower is also 0 times 1/2 minus, I could have done epsilon over 2, couldn't I? Minus epsilon over 4. Plus, and now my next term is 0 times epsilon over 2. And then my last term is 1 times 1/2 minus epsilon over 4. And then what do I notice? I notice that this term is 1/2 minus epsilon over 4. So what happens when I subtract the two from each other? So very simply, when I subtract them, when I subtract my upper and my lower, what do I get? I get this minus this, and all I have left is epsilon over 2. I guess I like the epsilon because that's less than epsilon. Okay, so so there we go. So I now so that means that this section is integrable, and so so like I said, we could shrink those down as small as we want, and it still works. But let's compare that to a function that we know is not integrable. Let's come back to this function that we all loved so much. F of x is going to equal 1 if x is a rational number, and 0 if x is not a rational number. And then notice this. If P is any partition, then let's not write all these out, but let's just think about it. Then what is the upper sum going to be? Well, any interval that we take, so any interval we possibly take, any a, b, contained in 0 to 1, you get that the max value is always going to be 1, because 1 is the largest it could be, and then the minimum value is always going to be 0. So our upper is just a bunch of 1s times, it's just the sum of the 1s times the delta xj's, but that's just equal to 1. Whereas our lower is the sum of a bunch of zeros times delta xj's, which is just 0. And so our upper minus our lower is always equal to 1, and we can't make this less than any epsilon. So if epsilon is, say, a half, then you can't do this problem anymore. Okay, so what we're going to find, and this is kind of one of the results that we'll slowly piece out, and again, if you really want to go look more and dig deeper into this, look into the Real Analysis 2 class, look into the idea of measure theory, and that'll really tackle this in greater detail. But what we're going to find is that the real important question is how many discontinuities that we have. And it turns out that as long as your discontinuities are separated enough, then you can take the integral, like that one discontinuity all by itself. Once you get where the discontinuities are, say, like dense, like this one was, then all of a sudden it doesn't work. And we'll do some interesting ones. I'll throw some at you in a little bit that kind of mess with us a little bit. Okay. All right. So let's come over here and let's finally define what it means to be an integral, and to be it, or what the integral value means. So when we write this symbol, what are we talking about? Well, we're going to have two terms. We're going to have the term that we call the L integral. The L integral from a to b of f of x dx. And what this is this is going to be the soup of all the lower sums, such that P is a partition. So it's the soup over all partitions of the lower sums. Similarly, we'll have U, which is the upper sum, and you might be able to guess what that one is, which is the inf of all the upper sums. Okay, So in other words, we took all of our lower sums and we took the sup of them, so we took the biggest one, and then we took all the upper sums and took the nth of them and took the smallest one. And what we'll see is that if the lower sum equals the upper sum, then that is what we're going to call our integral. Then that is what we'll call the integral from a to b of f of x dx. Okay, we should probably take a moment and convince ourselves that this is actually what it means. This is actually the same definition of being integrable as what we had a moment ago. And the answer is that it is the same definition that we had a moment ago. And what you can see, right, is that if the upper sums are less than epsilon, then the sup minus the nth needs to be less than epsilon. So these two have to actually be the same value. Now, what's more than that, if you can't make the lower sum and the upper sum within epsilon of each other, then that means you can't, then that nth and that sup are not going to be equal to each other because there's some space. And just like earlier in the semester, if there's space, you can always find some value in there that doesn't work. So this is actually equivalent to the definition that we had before. Okay, so this is kind of at the end of this first idea of how we're going to define integration. I'm going to come back with a second video in the very near future. And what we're going to do with that video is we're going to tackle the question of what about these Riemann sums we had in Calc 1? And so we'll tackle that and kind of show that the idea of using Riemann sums from Calc 1 ends up being equivalent to this idea. For some proofs, this way of talking about partitions and upper and lower sums is going to be the better way to prove theorems. For some theorems, it's going to be taking Riemann sums and taking the limit of a Riemann sum that ends up being the better way to prove a theorem.